Welcome back, everybody. We're on our last lesson for Chapter 8 with exponents. We're going to talk about exponential growth and decay. Let's warm up first with the percent change question. We're going to describe each as an increase or decrease and then round to the nearest tenth of a percent. So we're going to whip through this pretty quickly. The original cost of a shirt was $25. It's on sale for $22. So was that an increase or a decrease? Well, definitely a decrease. So let's find the percent change. So the way you find percent change is you subtract to find out how much did it change. It went down 3. And then you take the change and divide it by the original. So 3 over the original, 25. Now we can do a quick shortcut and make this 100 by multiplying by 4. And 4 multiplied to 3 is 12. So it was a 12% change, and it was a decrease, 12% decrease. In 1 week, a plant went from 15 centimeters up to 18. So here, this is increase. So this will be an increase. And again, let's subtract these. So 18 minus 15, this is also 3. And we divide by our original. Our original was 15. So 3 out of 15 reduces to 1/5, and we know what that percent is. That's 0.2, so that turns into a 20% increase. So just a quick warm-up for this lesson. All right, this is more of an informational slide, but I do want you to listen. So here it's the same formula we've used before, y equals a multiplied to b to an exponent. Except if we're doing exponential growth, a is the initial amount. So that's what you start with. And the base, if it's going to be a growth factor, okay? So this is our ratio, common ratio, what we're multiplying by. If it's going to grow, it's got to be greater than 1, because if I start with 5, okay, so maybe I start with 5 pounds of something and I multiply it by 1, well, I just stay at 5. I can't get bigger. So it's going to have to be greater than 1 to grow, and then I have an exponent. If we look at decay, very similar. We have an initial amount, so we start with something. Maybe we start with 5, but our base is going to be different. For decay, it has to be between 0 and 1. In other words, it has to shrink it. So if I half 5, 1/2 is between 0 and 1, and then I put my exponent on. Now when I multiply that, 5 will start shrinking and going down, where this one will start going up. On this slide, I just want to practice identifying what the A is, what the initial amount is, and what the B is, the base, which remember that's your common ratio. And then if it's growth or decay. So let's start with this one. There's nothing in front of our B. This is our B. There's nothing there. So if there's nothing there, it's an invisible 1. So the initial amount, they start with 1 in the pattern, and they multiply by 5 each time. So the pattern will look like that and keep going. And the base is 5. Now, look at our common ratio. It's 5. That's greater than 1. So this, and look at our pattern, it's definitely growing. So let's circle growth. Okay, let's try again. Here, our initial amount is 8. So we start with 8, and our base, or our common ratio, is 1/4. So if you think of it, you start at 8, and then you fourth 8 to get 2, and you fourth 2 to get a half. Boy, this is shrinking. So, and it makes sense because our base is 1/4, and that's less than 1, so this is decay. It's getting smaller and smaller. Another one to practice. So here again, I have a base with an exponent, but I have an invisible 1. So my initial amount's 1. This is less than 1. So what I'm going to end up with, see it's shrinking already. So I'm going to end up with 0.04, and it's small, so that's going to be decay. It's getting smaller. Last one. This is our initial amount 4, and our base is 2.5, which is bigger than 1, and because it's 2.5, it will grow. There will be a lot of word questions in your assignment for this, so let's practice a couple. So in 1998, the population of a small town in Minnesota was about 13,000 people. Since 1998, that population has increased, okay, so we have growth, 1.4% each year. So they multiply it by 1.4% each year and add it back in. So relate this to an exponential function. So we need to figure out what all our variables are going to be. We will start with x. X is the number of times we're going to do this, and so it'll represent the number of years since 1998. So we'll use this later on when we solve this question. Y. Y, this will be the population. It will be the population for whatever year we're looking for with x, okay? So when we solve it, that will be our answer. That will be the population. A is going to be the initial amount. So in this case, our initial amount was 13,000 people. Okay, that was in 1998. And B is going to be our factor, our common ratio, our base. We have to talk about this one. So let's talk about this for a second. All right, so I talked about that we have to talk about this common ratio, the base. All right, our percent is 1.4%, and if we make it into decimal form, it's 0.014. Now, this is the part. Because it's growth, we are going to have to add a 1 to this number. The reason is explained on the next slide, but the reason we're doing 1 is we have to count this 13,000 and add to it. So by multiplying by 1, we get 13,000 included, because 1 times 13,000 is 13,000, and we get to add that 1% each year. Let's set up our equation and solve it. Here's my equation that I set up. So my initial amount is 13,000. That's how many people were there in 1998. My growth factor is 1.014. I'm going to raise it to the 8th power, because if I do 2006 minus 1998, that gives me 8. So that'll be 8 years since the beginning. So let's use our calculator and figure this out. So when I did that, I ended up with 1.117. It kept going. Okay, do not clear your calculator. Do not round. Do not. Leave it in your calculator and multiply it to this. Then we will find the approximate population. So do that now. I ended up with approximately 14,529 people. It was 0.37. It kept going. So that's our first example. I do want to talk about the percent growth and decay and the adding 1 thing I did. So if it's growth, you need to make the percent a decimal by moving it 2 places to the left, and then add a 1 to the decimal. So 5% would be 0.05, add 1, that would be 1.05. So that's 5% growth. If we have 5% decay, we subtract the decimal from 1. So 1 minus 0.5%, and that gives us 95%. And the reason is, if you think of it like this, here's your whole amount, and you're going to lose 5%. It's going to go away. It's decaying. You're losing 5%. If that's gone, well, what's left? 95% of the original will be left. That's why with decay, we have to subtract from 1. Now we're going to talk about compound interest. Suppose your parents deposit $1,000 into a college fund and it pays 7.2% interest compounded annually. That means each year they're going to add that 7% back in. Find the account balance after 5 years. So let's set this one up. Let's see what I filled in here. So X will represent how many years we want to look for. In this case it will be 5, so we will use 5 for that. And then Y, that's how much money will be in the account. The money after X years in the account, our balance. That will be our balance. A is what we start with. We start with $1,000. And B is going to be our base, which is our common ratio, which will be our percent. Remember how I did this? I took 7% and wrote it as a decimal, so 0.072. And because the money is increasing or growing, I put a 1 in front. Now let's write our equation. Here's our equation. Y equals $1,000 multiplied to 1.072 raised to the 5th power. And the reason we use 5th power is they're doing it once a year for 5 years. So that's 5 interest periods they're doing. So they're going to do it 5 times if they did it by hand, but this is a shortcut. All right, let's solve this and see how much money would be left. So, first thing you do exponents. When I did that, I ended up with this. Again, do not clear your calculator. Don't clear your calculator. Multiply it to 1,000. Here it is. You end up with $1,415 and about 71 cents. I rounded. So, you know, 5 years you made $400. That's okay. That's pretty good. We're going to redo this problem that we just did. Same setup, 5 years, but we're going to pretend interest is compounded quarterly instead of annually. So let's talk about what that means. The interest will now be 4 times a year. So that means every 3 months, they're going to do this. Okay, they're going to give you money back into your account. So if they're going to do it every 3 months, that's 4 times a year. So first thing what we have to do is we have to find our new percent. Our old percent was 7.2%. It's right here, 0.072. But that's based on, that was a yearly percent. Well, if we're going to do it quarterly, we have to divide this by 4. So that's important, and this is a hard step. So use a calculator and divide that by 4. I end up with 0.018. So now I'm going to add the 1 in front. So 1.018. I'm not allowed to use that 7% because that's based on a yearly amount. And we're going to do this each 3 months, every 3 months. My new X value, that's going to be different also. And it's explained right here. 4 interest periods per year. So this is 1 year, but we have 5 years. So, 4, 8, 12, 16, 20. We have 5 of these. So what you have to do is multiply the 5 by 4 because that ends up with 20. There's 20 quarters. 20 quarters in 5 years, so we have to use a 20. That will equal X. Here's our old equation. This was our old equation. Now we're going to compare this to our new equation for quarterly. I still have 1,000, and I still have it multiplying to a percent with a 1 in front, but look at it, it's a lower percent because I'm doing it quarterly. Lower than this, but look at how many times I'm doing it, 20 times. So let's see what happens to our answer if we do it this way. We end up with $1,428.75, where on the other page we had $1,415.71. So this is, it doesn't look like much, but if it's a bigger percent and it's over a longer year or more years, it can add up, but the compound interest usually gives you more money in the long run. Okay, you get more money if you leave it in compound rather than annual. This one, you don't have to take any notes really on this page. I just want to talk about this. This chemical technetium 99 has a half-life of 6 hours. So suppose a lab has 80 milligrams of technetium, however we say it, 99. How much technetium 99 is left after 24 hours? So this, we don't have to solve it. We're just looking at what half-life means. So every 6 hours you have this, 80 milligrams of this stuff. After 6 hours, it's down to only 40, okay? But it takes 6 hours. So the first thing they did was, how many 6-hour periods are there in 24? So they did 24 divided by 6. And they found out that this will happen 4 times, okay? That's where that came from. So they basically divided by 2, that's what half means, half-life. They divided by 2 4 times. So it's kind of like this. They had 1/2 and they divided, or they multiplied by 80 by 1/2, but they kept doing it 4 times. So it makes sense. 80, okay, now we're at 40, and then after 2 hours, or 2 half-lives, now, not hours, half-lives, we're at 20, then half that, 10. So at the end of the day, they started with 80, they're only left with 5. It like shrunk. So this is total decay. We are going to do one of those using the formula. Suppose the population of an endangered species has decreased 2.4% each year. So it's going down, so we're going to do that special trick. Suppose there were 60 of these animals in a certain area in 1999. Write an equation to model the number of animals of this species that will remain alive in that area. So let's set it up. Okay, so I set it all up. X is the number of years since 1999. Y, our answer will be how many of these animals will be left after that time. And A is what we start with. And we start with 60 animals. That's how many were there in this area. Okay, the B is the tricky part. Because it's decay, we have to minus it from 1. So make this a decimal and minus it from 1. And we end up with 0.976. And again, think of it this way. Here's all the animals, all 60. 2% is going to be leave. That's going to be gone. So what's left? What's left right here? 97.6%. Now let's set up our equation. Okay, I set it up like this. 60 is what I start with. My decay factor is 0.976. Remember, decay is always less than 1 and greater than 0. And I'm going to do this 6 times because 2005 minus 1999 is 6. Okay, let's see how many of these animals will be left after 6 years. I took 0.976 and raised it to the 6th power, and I ended up with 0.864 and blah, 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 blah. Do not clear your calculator. Do not clear it. Now multiply to 60. We end up with about, I got 51.86, so 51.9, but because, it's going down, you kind of round down here. You can't have half an animal. So 50, I'd say 51. About 51 animals would be left. So you started with 60, now there's only about 51 left. We are going to try something completely different for the practice problems. Okay, what I want you to do is scan this or go to this website and you pick 3 problems from that little quiz from our book practice site. You pick 3 problems, this is important. In order to get credit when you turn in your note sheets, you have to show work for the 3 problems you pick on your note sheet. Okay, so in the space by here. Well, good luck. Bring any questions you have to class next time we meet. So again, go to this website. There will be 5 questions. You pick 3. Show work for them on the note sheet, and you definitely can submit and see if you're right. Take care. Bye.